Hello everyone, myself N. Uday Ranjan Goud, working as Assistant Professor in Department of Aeronautical Engineering, MLR Institute of Technology. So in the last module, we discussed about combined open and closed section beams, and we have seen a problem in combined and open section and closed section beams. Now in the present module, we are going to see what is twist and warping of the closed section beam. So usually the twist, when the torque is applied on the beam, the shaft, then it's going to twist. And if all the loads are consistent or symmetric loads, and it's not going to affect the cross section of the beam. But sometimes what happened when the shear loads that are applied not at the shear center, then they are going to create a problem and they are going to twist, and then the warping also is going to form. So the shear loads which are not applied through the shear center of a closed section beam, and they cause the cross sections of the beam to twist and warp, and in addition to rotation, and they suffer out of plane displacements also. Okay, so for example like this, and if you have an arbitrary cross section like this, and because of the shear loads which if they are not applied through the shear center, then they are going to affect the beam, and therefore what happens here, and you will get the bumps like this, that is they suffer rotations out of plane actual displacements. Okay, so these kind of warping in the cross section is undesirable, and therefore we need to study the effect of this twist and warping of the cross section. So the expressions for these quantities may be derived in terms of shear flow distribution Qs as follows. And since we know that the shear flow, that is Q equals to tau T, and therefore we also know the tau, that is the shear stress, is equals to modulus of rigidity into shear strain, and that we know from the basic formula of modulus of rigidity. Then we can express Qs in terms of the warping and tangential displacements, that is W and Vt of a point in the beam wall, by using the formula, that is Qs equals to Gt into dou W by dou S into plus dou Vt by dou Z. So this we have seen in the previous sessions, that the shear flow, that is Qs, is equals to Gt into dou W by dou S plus dou Vt by dou Z, where W is the actual displacement and Vt is the tangential displacement. That means we've written gamma as the shear strain, and that we have seen it is given by dou W by dou S plus dou Vt by dou Z. Okay, so and since we know that Q equals to tau into T, and then we replaced this tau as G into gamma into T, and in which again this G is we written as it is, and for gamma we are substituting this. So that is Gt into dou W by dou S plus dou Vt by dou Z is the shear flow, that is the shear flow distribution that we got. Okay, and also for substituting for dou Vt by dou Z from the previous sessions, and we have seen the what is for Vt, and then what is a formula for Vt that we have seen, that is P into theta plus U into cos psi plus V into sin psi, that we have seen in the previous sessions. And Vt is nothing but the tangential displacement, and then differentiation of that dou Vt with respect to Z, and you are going to get P into d theta by dz, and du by dz into cos psi, and then you got dv by dz into sin psi. Okay, so this is dvt by dz. So when you try to substitute in this equation, you are going to get Qs by Gt, that is equals to dou W by dou S, which is the first term, and then dou Vt by dou Z is nothing but this entire equation, so that we are adding here. Okay, so that is Qs divided by Gt, that is the shear flow distribution for this case. So now integrating this equation with respect to 0 to S, with respect to S from the chosen origin, any 0 to S you can consider, and noting that G may also be a function of S. So what we are doing here, integral 0 to S Qs by Gt into ds, we are integrating from 0 to S, and then the W, dou W by dou S is also integrating 0 to S, and then we get d theta by dz, integral 0 to S PdS, and then du by dz, integral 0 to S cos psi ds, dv by dz, integral 0 to S sin psi ds. So this is what the integration that we considered for the complete equation, which is taken from the origin 0 and to the region S. And if you try to write this one in the other form, you can write integral 0 to s qs by gt into ds, and this is also you can write similar 0 to s dou by w by dou s into ds and d theta by dz. So here we are going to write this one d theta by dz into integral 0 to s pds. Here we are writing the similar one, and here what we are writing here integral du by dz integral 0 to s, and what this we are writing the component cos psi ds, we are writing it as dx, and sin psi ds, that is the vertical component, that is we are writing it as dy. And therefore the formula for the shear flow distribution here integral 0 to s q by gt into ds, that is equals to, when you integrate this, you are going to get ws minus w naught plus, and this is nothing but the area swept out by the region, and you can write it as 2 into a naught s swept out by the region, and 2 a naught s into d theta by dz plus du by dz into this integration, you are going to get xs minus x naught dv by dz into ys minus y naught. Okay, so where a naught s is nothing but the area swept out by a generator and center at the origin of axis o, and from the origin for s to any point around the cross section. So continuing this integration completely around the cross section, that yields from the equation, that is cyclic integral of qs g theta by qs divided by gt into ds, so which you can write in the other terms as 2a into d theta by dz. And in fact, when you try to write d theta by dz, you are going to write, we have the formula d theta by dz equals to 1 by 2a cyclic integral of qs divided by gt into ds. Okay, so now substituting for rate of twist, so wherever we have d theta by dz rate of twist, we are substituting in this equation for shear flow distribution, and therefore from this we are going to write what is this warping distribution ws minus w naught. So substituting for the rate of twist in the equation and rearranging the terms, so we obtain the expression for the warping distribution around the cross section. So the warping distribution around the cross section, that is given by ws minus w naught, that is equals to integral 0 to s qs by gt into ds minus a naught s by a cyclic integral of qs by gt into ds minus du by dz into xs minus x naught minus dv by dz into ys minus y naught. So using the equations, what do we do here is we replace du by dz and dv by dz by its terms that are nothing but xr into d theta by dz and yr into d theta by dz. So replacing that here, du by dz we are writing it as minus yr d theta by dz, and replacing dv by dz as plus minus xr d theta by dz, so that we are writing here. And then we got the last two terms in the equation represent the effect of relating the warping displacement to an arbitrary origin, and which itself suffers actual displacement due to warping. So in the case where the origin coincides with the center of twist r, then the equation simplifies here, and then the simplified in this is the special case where the origin coincides with the center of twist. Okay, so if that is the case, then the warping distribution further reduces, and its the equation is given by ws minus w naught is equal to integral 0 to s qs by gt into ds minus a naught s divided by a cyclic integral of qs by gt into ds. So when the center of twist r coincides with the origins, then it will not have any kind of coordinates and x and y coordinates, so therefore straight away this can be substituted as 0, and you left with this warping distribution formula. So this is the warping distribution formula that can be used in the formulas along with the twist, and usually you will be getting the questions in the examination, like he'll ask you to find out the twist of the section, and followed by he may ask you to calculate the warping distribution. So if that is the case, then you have to utilize this formula, use this formula according to the center of twist condition, whether at the center of twist coincides with the origin, or if it is not coincides with the origin, then you may use this formula. If it is coincides with the center of the twist, then you can use this formula, and you can just deduce what is the warping distribution for the given section of the beam. Okay, so this is what we discussed about the warping of the cross section. And the warping, the another one is nothing but, for example, if this is for the constant shear flow, and if you have a varying shear flow, and the equation slightly modifies here, so the warping distribution produced by a varying shear flow as defined by equation for axes having their origin at the center of twist. And if it is also applicable the case of constant shear flow, thus we can write it this as Ws minus W naught, that is equals to Q integral 0 to S ds by gt minus A naught S divided by A into Q cyclic integral of ds by gt. So what we are doing here it is, and we are trying to put in the form Q we can write as T by 2A from the torsion equation, and T by 2A we are writing here, and that we are taking common here because here also we have Q, and then the equation for integral 0 to S ds by gt can be written as delta OS in terms of delta OS, and then it should be multiplied and divided by delta. And similarly for here also integral of ds by gt you can write, and when you try to take common, and you are going to get here ws minus w naught equals to T by 2A delta into delta OS by delta, and then here this is a cyclic integral, and then you can write this as A naught S divided by A, and where we use the symbol here delta, that is equals to cyclic integral of ds by gt, and delta OS is nothing but integral 0 to S ds by gt. So this can be substituted in the formula, that is it is just replaced. Okay, whatever the distribution formula here we are having for warping, and that has been replaced in terms of deltas and rewritten this equation where delta and delta naught S are given by this formula. Okay, so the sign of the warping displacement in this equation is governed by the sign of the applied torque T and the signs of the parameters delta OS and AOS. Okay, so that's all from warping and twist and warping of the cross section for this unit. Okay, so let's see the other session in the, that is next topic in the other session. So thank you everyone for watching.